All right, folks, welcome to week 3 of Computer Science 2. So this week is mostly about the basics of object-oriented programming, or OOP. This should be still mostly a review from stuff that you saw in CS1. You should have at least seen a few of these things. Most likely you didn't have, like a homework assignment or anything where you really had to sort of code your own classes and sort of make them work and stuff. We'll have a little bit of that, of course, in this class for homework or lab-wise, but the most sort of interesting place that you're going to be using this is your final project. So a lot of this class is dedicated to these OOP concepts. So we'll have sort of this sort of mostly review, or what should be mostly review this week, and then we'll move into some of the more advanced topics next week and afterwards. So I wanted to just start off today with what we've done so far. So until now, we've really been using what's more commonly known as procedural programming. So the flow of our programs typically are, take in some data, do something with the data, maybe do something else with the data, and then get some output. So this idea is very common in a lot of sort of beginning programming, and even the sort of programming that I did with say scientific applications. There's nothing wrong with this style of programming when that's really what you need to do. Take some data, do something with it, and get some output. And typically that means setting it through some methods and all that sort of thing. So it's really verb oriented. You tell the computer, do this, do that, and then print out the results. But when you're thinking of a more large scale application, so think of how your operating system runs, or think about I'm using Adobe Reader to show the presentation, right? Think about how that program works. It's not simply I'm taking in data, doing some things with it, and then getting an output and the program's done. So for large scale applications, or sort of larger applications that folks are going to be using potentially every day on their computers, it's useful to have a different sort of paradigm to how to actually go about coding these large applications. So just an example idea here. Say we had some palindrome method. It's similar to homework type stuff. So we had this palindrome method. We read in some data, and it can be just as simple as typing in some text into the console. And then we do something with the data, determine if it's a palindrome, true or false, and then we get the actual output, in this case, of just a string. So it can be just that simple. It doesn't have to be procedural programming. It doesn't have to be some more complex thing. So the main sort of paradigm of programming, the main sort of idea of what you're going to be doing in the future for your larger applications is object-oriented programming. This is based entirely on data types. So you identify things that are part of your problem domain, whatever application you're trying to create. Those things can be as simple as sort of physical things. So we're going to work on our blackjack game, probably starting next week. And those things will be stuff like a card, or a deck, or a hand, or a player. So physical things that are part of the problem that I'm trying to solve, the application that I'm trying to write. Now, those things, the card, the deck, the hand, they know about their data. Those are called instance variables. So an individual card, a thing, is going to know what its value is. If we were using some graphics with it, it would know what image it was supposed to display on the front and on the back. So it would know about its own data. And then those things do work on their data. For instance, thinking about the cards, we might have a method that will flip the card from face up to face down. And so the data that would change is what image is being displayed, the front of the card or the back of the card. So when you first think sort of object-oriented programming and what is an object, what are these things, it's easiest to think of them as physical objects. What does a physical object have? What data does it have? And what can it do? A card can be drawn into the hand. A card can be discarded. A card can be flipped from back to front. Those sorts of ideas are what you want to think about when you first are sort of getting a good grasp on object-oriented programming. Now, if you look up OOP online, typically you're going to see sort of four, it's sometimes some of these are combined, but it's 3 or 4 main sort of words, main ideas associated with OOP. They're encapsulation, abstraction, inheritance, and polymorphism. Coming up, I have a slide, just sort of one slide on each one. And then we'll dive deeper into a couple of them today. Inheritance and polymorphism will come a little bit later on in the semester. So we'll focus a little bit more today on encapsulation and abstraction, but then we will get into the others in the near future. So the idea of abstraction is to only show the essential features of the application while hiding the details. I want you to think about a computer. So the computer you're using right now, whether it's a desktop, whether it's a laptop, it has a whole bunch of components. There's lots of components in there. If you've ever built your own computer before, you know that you bought a bunch of pieces. You bought processor and motherboard and graphics card and all of this stuff. When you press that power button, hopefully the computer turns on. Right? If you're building your computer, you sort of cross your fingers the first time you turn the computer on. But when you press that power button, it turns on. But there's a lot of other stuff happening behind the scenes. There's lots of other stuff happening behind the scenes. At sort of a electrical engineer level, there's lots of voltages that are being run through motherboard and the RAM and the video card, and so you're drawing power, and then there's obviously lots of capacitors and resistors and all sorts of things on the motherboards. From an electrical engineering level, there's a lot of stuff going on, a lot of important things happening to turn your computer on. But from a user level, from someone who's sitting there at their desk and they press the power button, we don't really need to know what's going on. We just want to press the button and the computer turns on and we start working on it. So it's a similar idea, this abstraction idea. We don't need to know all the details of everything that's going on in the computer when we turn it on. So it's mostly all hidden from us. We just have to be able to use it when we want to use it, using a simple interface, a power button. So that's one of the questions you want to ask. Do you really need to know what happens in the computer when you turn the power on? So in Java, classes provide methods to the outside world that allow access and use of their data variables. So classes will be providing our interface, like the power button. Think of the power button as a method inside of a computer class. The computer has a whole bunch of components, has a whole bunch of data associated with it. It's a thing from object-oriented programming. A power button would be a method. I call the power on method and the computer turns on. The data will remain hidden. And we'll talk about how we get abstraction, what we have to do in our actual code to have abstraction in the future. But this is a sort of a thing I want you to think about. The data is going to remain hidden, and then we provide classes and methods to allow us to achieve this abstraction and allow people to interact with the classes that are outside. All right, encapsulation is sort of the other one, and it's one of the other main ones we're going to talk about today, and it's related to abstraction. It's all about binding data and methods together in a class. A class is supposed to represent a thing. So those data and the methods that you combine together, they're all related. So that card example, the value of the card, the picture on the front and the back, all of those things would be bound together in a card class. And that represents data. It's just more complicated type of data than a single integer or a single double. The client, whoever is using this card class, which oftentimes will be you. You will create a card class and then you will use the card class to do things. You will use it as a black box. You don't have to know how it works. If you coded it, you probably will know. But if you didn't code it, if you gave your card class to someone else and then they were just going to use it, they don't have to know how it works internally to be able to use the class itself. So encapsulation and abstraction gets us to that point. That's why these are very closely related. There's this thing called an API, and it specifies the contract between the client and the class. The API is the application program interface. This is something that you'll see online. You'll see sort of APIs for all sorts of different things online. It essentially tells you these are the things that you can use from this class or from this set of classes. So we're going to talk just a little bit deeper about this. I have another slide sort of doing a simple example of sort of what this API thing means and what I mean by contract between the client and the class. The bottom line when it comes to this sort of encapsulation and abstraction idea is that you don't need to know how a data type is implemented. In other words, you don't need to know how the class is coded to use it. And you've been sort of following this, or at least using this idea, since the very first time we did a print in Java, because you're using system.out.printf. Do you know how printf works? You know how to use it. But how it works underneath? Probably not. What about scanner? We've been using scanners for most of the time for CS1 and in CS2 for most of our assignments. But you don't have to know how it works in order to use it. That's the idea here. And that's something that you'll be sort of seeing that a lot as we go through the rest of the semester, where you'll be using certain classes that you don't necessarily understand how they work inside, but you can use them to do things like, say, make a game in Java. All right, so here's this idea of the sort of client and API and implementation thing. So we have a client. This is Calvin. My PhD advisor would always throw Calvin into his slides. His name happened to be Calvin, so I sort of keep that tradition alive here and throw some Calvin every once in a while. So we have our client Calvin, and he wants to use his television. Following this idea of abstraction and encapsulation, he shouldn't need to know about how the TV was implemented. He shouldn't have to know the specifics of the refresh rate and the physical characteristics, like if it's wall mountable or not, or what type of monitor it is, or any of the other sort of myriad of properties that a TV has. He should only have to know how to use the remote control. So the client just needs to know how to use the API. The API in this case would be you press a button and the volume goes up or down. You can change the channel. You can adjust the picture. You can do any number of things that you would normally do with a remote. But Calvin should only need to know how to use that remote. He shouldn't have to worry about the internal workings of how that happens on the TV. When he presses volume up, what happens internally on the TV shouldn't matter. The volume should just go up. And that's usually what we experience when we're using a television. We don't have to worry about all of the internal things that are happening. Now, the manufacturer of the TV, the one who implemented the TV, they need to know what API to implement. You wouldn't buy a TV where you weren't able to change the volume. So they need to make sure that as part of their process of making the TV, they have a way for the volume to be adjusted. So the implementation or the implementer, from back to the sort of coding idea, the one who is coding all of these classes should know what API to implement, should know what people are going to need if they want to use their class. So we think back to the card again. I should be able to flip the card from back to front. That's something that I should program as the implementer. Someone who wants to use my card class should be able to just flip the card front to back or back to front and not have to worry about how exactly I did that code. So the implementation or the implementer needs to know what API to implement. So hopefully that sort of makes it a little bit clearer with this sort of API sort of thing and there's sort of a contract between the client and the class. That's what this is. This API is essentially the contract between the client and whoever wrote our code. We'll talk about inheritance and polymorphism coming up in the future in much more detail. but I have just a single slide on each one that'll just give you a little taste. Even if you don't fully understand it yet, you certainly will after we really do a deep dive into it in the coming weeks. So inheritance is a way to reuse code over and over again. And one of these ideas that I've sort of mentioned in CS1 and CS2 classes is that if you find yourself copying code, like copying and pasting code from one place to another in your application, then there's probably a better way to do it. So inheritance is another way to reuse your code from sort of multiple different ways. Typically, you start with some base class that's going to contain data and methods. So you start with just a class that has data and methods in it. And then you create derived classes that inherit from the base class and are able to use any of the methods or the variables defined in that base class. We'll see how to do that in code and sort of the keywords that go along with it and sort of what that means. But the little picture I have here shows sort of a bicycle class. And typically your base class is very generic. A bicycle is very generic. There are lots of different types of bicycles out there. That's our base class. You may also hear me call this a superclass or a parent class. They all mean the same thing. Well, I could create some derived classes or subclasses or child classes that are specific types of bicycles, like a mountain bike, a road bike, a tandem bike. These bikes all have some of the same properties. Typically, they're all going to have two wheels. They're all going to probably have some kind of gearing system. So they're going to have similar properties, but a mountain bike may have shocks on it, whereas a tandem bike is probably not going to have shocks on it. A road bike might have different types of tires, much thinner tires, might have very different handlebars. A tandem bike is going to have more than one seat. So they're different variations on a bicycle. And in our code, we can represent that using the variables and methods from the regular bicycle class, and then making some modifications to make it a mountain bike without having to rewrite all of the code that we wrote in the base class. So we will see lots of this in the future. And in our card game, our blackjack card game, you will see lots and lots of inheritance. So we will be talking about inheritance quite a bit. All right, the other concept that we'll talk about in the future is polymorphism. And it is tough to come up with sort of a one-sentence phrase that defines what polymorphism is. The way that I used it in sort of scientific programming, for example, sort of dealt with GPU implementations, so something to run on your graphics card, and CPU implementations. So we would write our code, and we would write a way for it to run on the GPU, and we write a way for it to run on the CPU. And without changing any of our underlying code, we could let our application pick at runtime which one to use. That may not sound sort of that awesome, but it allows you to do things where you don't explicitly have to say, I want to run this version versus this other version. It lets your program pick at runtime, which is quite and sort of amazing concept. So it lets us essentially process objects, which remember are essentially classes, differently depending on what their underlying type actually is. So there's some really cool stuff we can do with it. You sort of define a generic interface, and that interface can hide multiple underlying implementations. So there's some really cool stuff we can do with it. It's not until you really dig into how it's done and what it means in some of your code that it starts to make sense. And we will be using polymorphism in our blackjack game as well. So you will see some of it there, not just in a few slides on a presentation or something. Okay, so those are the four sort of main concepts that you're going to see a lot of this semester when it comes to OOP. So let's actually mess around with some classes. Let's talk about what a class is and how we can actually write our own. So classes are blueprints for objects. So classes and objects are two different things. They're related, but they're two different things. So classes are the blueprints. They define the data fields and the methods that an object of that type can have. Creating an object from a class blueprint is called instantiation. If you see something where someone talks about like the instance of a class or an object of a class, those mean the same thing. So when I create an object from a class blueprint, think of that object as the physical thing. So I know what a card should be. That's the class. When I actually instantiate a card object, that's the object. So just like the blueprints here of our starship, I can have something that defines what the starship is. But it's not until I actually build it that I actually have an object of that starship. I'm going to show you some class diagrams. And if you've looked at the Blackjack document, you've seen a whole bunch of these types of diagrams. This is a very simple one. I'm going to show you the sort of more standardized version here coming up in a few slides. But this will give you the idea of what a class contains. So a class always has a name. The class will have some data fields, and typically it will have some methods as well. If I instantiate an object from the class, then the object will have a name and it'll actually have values associated with the field. So here, maybe I create a circle of radius 1. I'm not restricted to just one object. I can create as many as I want. I have the blueprint, so I can create many, many more. So maybe I have another one that I want to call object 2, and its radius is different, radius of 5. And another one, radius 25, and so on. Just like if I had a card blueprint, I could create 52 different cards, and then I would have a deck. So that's how you can sort of create sort of a relatively small amount of code to give you many, many different options for what the individual objects can be. So the anatomy of a class that you can write looks like this. You always have the class name that's always going to be like class and then the name, so the circle or something. We'll have the data fields. These are typically at the top. You're always going to see me code them at the top. You always have a constructor. There are ways to get around having a constructor, but typically you will write one even if it's empty. And then we have methods. So here we have get area and set radius. We have this public double radius equals 1. I do set it to a value here. We'll talk more about that in the future. One thing I want you to notice about this class, and this is a full class. This class will work properly. There's nothing missing from this, is that there's no main. There's no main here. Every time we've made a new file in a project in class, we've always had a public static void main. But now there's not. So remember what main does. It's where you start the program. Well, our circle here isn't where we want to start the program. This is just a blueprint for what a circle object is. So there will not be a main. So if you think of your program and you think of the things that are part of your program, those things don't need a main because they're not where your program starts. So in your entire application, you will only have one main. And typically it'll be in its own class. It's not going to be in like a circle class like this. So that's something that I want you to remember. When we're creating a blueprint for a thing, circle, a card, a starship, it's not going to have a main. All right, so UML diagrams are the standard sort of diagrams for describing what a class contains. It's not going to show you implementation. It's not going to show you what code is in the methods, but it will give you an idea. And oftentimes, if you can sort of figure it out, if you know what the methods are supposed to do, you could probably write some of them yourself. If you look at the Blackjack game document and you see what the method names are, you might be able to figure out how to code most of them by yourself, or at least figure out a way to code them. So it's just a standard way to represent classes and objects. So for example, that circle class that I just showed you would look like this. It has one field. It's called circle. It has one field called radius that is of type double. It has one constructor called circle. It has get area that returns a double. It has set radius that takes a double and returns void. So this would be the diagram for that class that you just saw. If we instantiated an object from that class in UML, it would look like this. It would be the name of whatever the object was, so circle 1, and it is a circle, and it has a radius value of 1. So if we created an object, this is what it would look like. So UML is very common. There's lots of programs out there that'll like analyze your code and take your code and turn it into a UML diagram. I used a specialized language to make the ones for the blackjack game, and typically in the slides I'll sort of show them more or less like this, which is just a few boxes and then the text in them. So you'll see them in sort of different sort of format, sort of looking ways, but for the most part you'll be able to sort of dissect what the UML diagram means just by looking at it, because they all have the same sort of style of format. They have the name, the fields, the methods. So let's talk a little bit about constructors, and then we'll hop into creating our own class. And I'll hop into Eclipse. So invoking a constructor is what creates the object. It constructs the object from the blueprint. And you've been using constructors for most of CS1 and also in CS2. Pretty much anytime you see the new keyword, it's invoking some kind of constructor. So as an example, with that circle class, this would be creating a circle object. We have the type, the name, equals new circle. We've done this before when we created, say, scanners. Scanner input equals new scanner. That's invoking the constructor. And here we're invoking the constructor in the circle class that I showed you a couple slides ago. The constructor must have the same name as the class. That's the requirement. It has to be the same name. And it doesn't have a return type. There's no return type listed, not even void. So this void circle, this is not a constructor. It will work, but it's not considered a constructor. So you can have it in your code, but it will not work as a constructor. When the constructor is invoked with new, that's what initializes the object. Because typically your objects are going to contain a bunch of data. And with a constructor, you probably want to set that data. So when you create a scanner, when you say scanner input equals new scanner, and then you put system.in in parentheses, that's initializing where the input is going to be coming from. Just like we talked about with the file IO last time, you put a file in there and then the input's going to come from the file. So it plays the role of initialization. That's the point of a constructor. So let's actually go in, let's actually create a class. Before that, real quick, what happens if you don't provide a constructor? Java will give you an empty constructor if you don't provide it one. So you don't have to give a constructor, but most of the time you'll want to. In fact, you'll probably want to just include it automatically anyway, even if it is empty. That way you always remember that there must be a constructor here. All right, so let's write a rectangle class real quick. So we saw sort of a circle class version. Let's do a rectangle version. So we need a file called rectangle.java. So in the Eclipse that I'll switch to in just a second, I just have an empty project. So we'll start with an empty project. We're going to include two fields as part of this rectangle, a height and a width. We're going to add a constructor that plays the role of initialization. It's going to set the height and the width. And then we're going to include a method called getArea. And this is going to return the area of that rectangle. So it's not going to be a lot of code, but it's going to show you that we can create a blueprint very easily for what a rectangle is. And then in a little bit, we will create a main that will be able to instantiate rectangles from. The UML diagram looks like this. Name is rectangle, height and width, they're going to be doubles, a constructor that doesn't have any parameters, and a getArea that returns a double. So let's go ahead and do that. So we'll switch over to Eclipse. I just have an empty project. So I'm going to right click in here and create a new class, and I'm going to call it rectangle. I'm not going to include a public static void main because this isn't our main. This isn't the class that's going to contain main. It's not the class that's going to start our program. It's just a blueprint for a rectangle. So I'm going to create a rectangle, say finish, and here's my class. So this is all I need to start with. We can just keep this the same, public class rectangle. That's exactly what we want. So we have the name. Now we need the fields. That's the first thing that you're going to put. You're going to put this data in there. So I'm going to create a, let's see, we'll talk a little bit about visibility here in the future. So we're going to leave it off for now, but I'm just going to create a double called height and a second double called width. So 2 fields. These are class variables. When we talked about scope previously, these are class variables. I can use these in any methods that I write in this class, and that will be important as we go forward. All right, so I have my fields. Now let's write the constructor. Maybe I'll put the comment here. So I'll write my constructor. There's no return type. So you don't put void, you don't put double, you don't put anything like that. And it has to be the same name as the class. So I'm going to say rectangle. It's not going to have any parameters, and it's going to initialize height and width. So I'm going to say height equals, in this case, it doesn't matter what it is, but I'll say 7, and maybe the width is 5. So when I create this rectangle, it will automatically set the height and the width to specific values. And then I can have my methods. So we're going to create a public double. It's going to return a double, get area. No parameters. And all this is going to do is return the height times the width. The height times the width. That's all it'll do. Now notice I didn't put public static. When we've been writing methods that were sort of associated with main, we always would say public static and then we would throw stuff in. In your classes, so your blueprints for objects, typically we're not going to do that. We're going to talk about what the static keyword means next time. So in the second lecture, the second sort of review-ish lecture for OOP. So we will talk about that in the next lecture. But when you're writing your blueprints, you don't need to put the public static unless you're intending to. And that's what we'll talk about, sort of when that's useful next time. So this is it. This is a class that we can create an object out of. So a little bit later, we will actually do that. We will actually write up just a little bit of creating this object after I show you how that works with our circle. All right. So back to the slides. I do have the sort of answer here. It might be slightly different than what I wrote in Eclipse, but it should be pretty close. All right, so now we should talk about object references. How do we get access to this data and these methods? Because if we want to do anything with our object, if we want to know what's the area, if we want to call that method get area, how do we do it from elsewhere? How do we do it from our main method or our main class? So objects are always accessed via their object reference. So their reference is whatever you name them. So I might say rectangle R1. R1 would be the reference. Just like when you create a scanner, you say scanner input equals new scanner and so on. Input is the reference. And then you can access its methods via the dot operator. So when we say, for a scanner, we say input dot next int. Next int is a method that is part of scanner, and we are accessing it via the object reference. So if we were to do this with the circle that we talked about earlier, we would create our circle. So our object reference would be circle 1. And then if we wanted to access the radius value, we would say circle 1 dot radius. And then it would tell us that we could do something with this in a calculation, we could print it out, anything like that. So because radius is an instance variable, meaning that it depends on the specific circle, this is how we access that radius. So we could create lots of circles with different radii. So that's the idea of this object reference. It's just what you name it, but it is technically the object reference. All right, so here is a slightly different version of that circle. I added in a constructor, another constructor, second one. Constructors follow the same rules as overloading methods. We can overload constructors. In other words, we can have more than one of the same name as long as the parameter list is different. So here we've got one circle that takes no parameters, and here we have a circle that takes one parameter. If I use the constructor that takes one parameter, I put a number in here, and that's what it sets the radius to. Although I did sort of potentially have an issue here. And it's something I want to point out, because remember, constructors are what initializes the object. It's what sets all of the data, or at least what should set the data. Notice that the radius, I don't give it a value here. It's just the radius. The second constructor sets the radius based on whatever you entered. But if I use the first constructor, what's the radius? It never gets set. The object is created, but the radius is never actually set. That's typically a bad idea. You want to make sure that the data that needs to be initialized is initialized in every constructor that you have. So to fix that, I could set here radius equals 1 in the constructor that takes no parameters. So now if I use circle with no parameters, it sets a radius of 1. If I use the constructor with a parameter, it sets the radius to whatever value I send in. This is a much better way to write this, this class, making sure that I initialize the radius in all of my constructors. The UML diagram for this would look like this. We still only have a one radius. Here we see two constructors, one with no parameters, one with a single double parameter, and then we have our set area and our set radius. So if we were to code this up and then use it, here is main. So the class here is just circle test. It's just the class that I'm writing that contains the main method. There's a couple things going on here. I'm instantiating first using this first constructor. So notice no parameter, no argument going into the constructor for the circle. And then I'm printing it out. Notice what I'm doing. I'm accessing that data, circle1.radius, circle1.getArea. So I'm using the reference, the dot operator, and then calling those individual pieces in my circle object, the getArea and the radius. Here's the second one. So I'm creating a second circle. So now I have sort of two of them in my code. This one, I'm sending in a value, 25. And so this circle would have a radius of 25, which means when I called circle2.radius, it would give me a different value, and circle2.getArea would give me a different value. So it looks something like this. So we're going to do this real quick with our rectangle as well. So you can sort of at least get a little bit of a class sort of started where we can mess around with our rectangle. So back to Eclipse. I'm going to create a class now that contains main. So I'm going to right click on my project, say new class. This one, I'm just going to call this one main with a capital M. You don't necessarily have to. You can name it really whatever you want to. But I'm going to make sure it uses public static void main. So when it opens, you'll get this. So that's my main class. This is where the program will start. Now, because rectangle is in the same project, I can just use rectangle. That rectangle class exists in my project. I can just use it. So I can do something like this. I can say rectangle. Let's say R1 equals new rectangle. That's calling the constructor. As soon as I run this line, the constructor will run, set the height and the width for R1. So now I can do whatever I want to do with R1. So let's say I want to do a print. So let's say I want to say system out, printf. Let's say I want to do, let's say I want to say the height and the width. So I want to say height, and I'm going to print out a double with maybe 2 decimal places, and then I want to do width. And do that again. And a new line. So for my args here, I'm going to use r1.height. And even the autocomplete does show this for me. So Eclipse knows what is available in my rectangle class. And I'll say r1.width. So I created r1. It has a height and a width value. I'm using those and printing it out. So when I run this, I get height is 7, width is 5. So that's how I'm accessing the height and the width from the object. Remember, this file, this rectangle file, is just the blueprint. It's not until I actually create a rectangle like this that one is actually created. We can do another print here where we mess with the area as well. I can call one of the methods. So I can say area, %.2f, and then a new line. So I'm going to call r1.getArea. So that should print the area as well. And I see the area is 35. So when you're thinking about what this is, what this R1 actually is, I want you to think about it as a physical thing. Just like if I were to create a card, or if I were to create, whatever, the 3 of diamonds. It's that sort of thing. It's not just a generic card anymore. It's a 3 of diamonds. Just like this rectangle isn't a generic rectangle, it's a rectangle with a height and a width. And then, of course, the ability for me to compute the area based on that. One of the things that we'll talk about in the next lecture is printing out just the reference. So let me show you what that looks like. So what if I just print out? I want to print it out as a string. This will be a little bit clearer when we talk about it next time. But I'm going to try to print out R1 as a string. So here I was printing out the individual values because get area returns a double, height and the width were doubles. So I was printing in these out at 0.2f. But if I just try to print out R1 as a string, let's see what happens. I get some sort of interesting value printing out here. If you ever see something like this, typically that means you're trying to print out an object as a string. This says rectangle. That's the type, because this is R1 is a rectangle. It's a rectangle at, and then a number. And this is a number. It's a hex number. And it's actually the memory location where this rectangle object is located in memory. So it's actually some interesting information. Probably not that useful, but it is sort of interesting nonetheless. One of the things that we're going to see next time, the next lecture, is how we can customize what happens when we do this. Because right now, if I want to print the height and the width and the area, I have to write a lot of code. I have to write some either a couple print statements or sort of just have a really long line of code to actually do that print. So we're going to see next time how we can get this to do what we want. Print out some information about the rectangle rather than just what the class is and where it is in memory. All right, so hopefully that sort of gives you a very basic idea of what a class is, how to write a simple class, and how to at least start thinking about using it. In our blackjack game, the card class will look very similar to the rectangle class. We'll have a couple of methods. We'll have a couple of pieces of data. We'll have one constructor, and that's pretty much it. It's not going to be that large of a class. It's not going to be a lot of code. It's how we use it later to form a deck and then to form, the player's hands and how we deal with it, how we use it later, that's going to really make our blackjack game work well. All right, so next time is more OOP. we're going to keep going with what we've done today. We're going to keep going with that rectangle class a little bit, and we'll talk about things like visibility and toString and a few other concepts that are associated with all of this. So that is all for now, and I will see you guys next time.